Hi, folks. We are going to take a look at section 7.3 today. Now, friendly reminder, this is the first section that will be in the second unit. So this is not on exam one. Okay, so this content not on exam one, but rather will be the start of the information for exam two and unit two. Okay. All right, so 7.3 is all about maxima and minima. And what we're going to do is take a look at how we might find sort of the highest point or the lowest point on a graph. And we sort of collectively call these critical points, okay? So we're going to use those partial derivatives that we reviewed last time to take a look at how to find critical points on a graph. But in particular, we're looking at how to find it on a three-dimensional graph, okay? And then we're going to review something called the second derivative test, which will help us determine what kind of maxima or minima, like what's happening at a critical point, okay? Now, this might be familiar from your Calc 1 class, so might be a little bit of a review, but hopefully it'll remind us of some important things before we officially launch into the second unit. All right, so I'm a big visual learner. I like to start with pictures. And when we talk about local extrema in 3D, they really take sort of three different forms, okay? So if we take a look at figure A over here, all right, I hope we can tell that we kind of have like an upside down cup or an upside down bowl, all right? And this point up at the top, that is what we call a local maximum. Right? In other words, it's the highest point on the curve in that particular region. Now, there might be higher points somewhere else, but in that immediate region, it is the highest. Now, similarly, if we take a look at the second diagram over here, B, this one, we can see that we have like a cup that's facing regular, the regular way a cup might face or a bowl might face. And we call this one a local minimum. Okay, so at the bottom, we have a place where the slope is 0, and it happens to be the lowest point in that region, so we call it a local minimum. And then last but not least, we have something that if you've ever eaten a Pringles potato chip might sort of remind you of a Pringles shape, all right? But it turns out that when we're in 3 dimension, we don't just have a local maximum and a local minimum. We have something also called a saddle point, okay? And a saddle point, we call it a saddle point because if you've ever ridden a horse, maybe at like a fair or something like that, it looks like a saddle that you might put on an animal that you were riding, okay? But what makes it a saddle point is really important. This is considered a saddle point because in sort of this direction, our x direction, okay, because our x-axis is this way. In the x direction, it is the highest point in that area. But if we looked in the y direction, and I'll switch to the highlighter, right? In the y direction, that same point is actually the lowest point of that particular region. So a saddle point is really what happens when in one direction it's the highest point and in the other direction it's the lowest point. Okay? All right. So these are the three main types. We've got a local maximum, a local minimum, and a saddle point. And if we wanted to use some fancier notation here for the local maximum, okay, we might say that our f of a, b, okay, meaning the z value or the function value there is greater than or equal to f of x comma y, all right? Meaning the point we want is larger than all the other points around it. Now, if we try and use that same notation for the local minimum, we might see something like this. f of AB is actually less than or equal to everything around it, f of x, y. Okay. And then for the saddle point, we can't really say either one of those because it's not a max or a min. It is the maximum in one direction and the minimum in another direction. Okay. All right. So local extrema, those are what those are called. It is a local extrema if we can find our partials. So we can find an fx and we can find an fy, and our fx at that point is equal to 0. And our fy at that point is equal to 0. Okay, so we have to be able to do both of those things, fx and fy both equal 0. Okay, now as promised is going back to like, okay, well, how do we know whether it's a maximum, a minimum, or a saddle point? And it turns out to figure that out, we use our second derivative test. Okay. And this second derivative test, we'll go through an example, requires us to find some second partials. But once we find those second partials, we can go ahead and think about 4 specific cases. Okay. So case 1, if we find our second partials, we plug them into a formula and we get that it's greater than 0. And our A, which happens to be our fxx, is less than 0, then we have a local maximum. All right. But in case number 2, if the second partials, and I'll tell you what that, I'll show you how to use that formula. If that is greater than 0, but our fxx is greater than 0, then it turns out we have a local minimum. And then case 3, that same formula we've been using, let's say we plug in our second partials and we get a negative number, that automatically tells us that we have a saddle point at that location. Okay, now those are going to be the 3 cases that we really focus on. There is a 4th case, and I just want you to know what it is, but it turns out that if you plug your second derivatives into this formula and you get 0, honestly, all that tells you is that second derivative test fails. All right, so we don't have enough information. We don't know if it's a local maximum, a local minimum, or a saddle point. Okay, but we are going to be focused on the first 3 cases. So the questions we will work through, the questions in your homework, should all be ones where you don't get 0 out. Okay. All right, one last thing before we head into some examples. All right, A is our fxx. C is our fyy, and B is our fxy. Okay, so that'll be important for us to know in a little bit. All right, let's take a look at this example. The directions say find all local maxima, minima, and saddle points of this multivariable function. So we've got fxy equals negative x squared minus y squared plus 6x plus 8y minus 21. Okay. Now, what do those steps say? Let's go back and read those a little bit carefully. Okay. So we have a function. That's good. We already have that. Let's first find out where our critical points are. So we're going to find where all the critical points are, and then we're going to use this case 1, case 2, case 3 to sort the points into whether they're a maximum, a minimum, or a saddle point. All right, so let's get started. All right, so step 1, we are going to find our critical points. And when we say that to ourselves, we're really thinking we want to see where fx and fy both equal 0. Okay. So let's take our fx. All right. First term, negative x squared becomes negative 2x. Negative y squared goes to 0 because it doesn't have any x's in it. So y is a constant. 6x becomes plus 6. 8y and the minus 21 both go to 0 because they don't have any x's. Okay, so really we have negative 2x plus 6. All right, now let's take our fy. Okay. Fy, we're going to go through the same function, but now we're treating x as a number and y as a variable. So derivative of negative x squared is going to be 0 minus 2y, because 2y is the derivative of y squared, plus the derivative of 6x is 0, plus the derivative of 8y is 8, minus the derivative of negative 21 is 0. And when we clean that up, we get negative 2y plus 8. Okay? So we've taken the first step to finding our critical points. We found our fx and we found our fy, but we need to make the fx and fy equal to 0. That's how we find our critical points. So my next step, I'm going to say 0 equals negative 2x plus 6. And I'm going to do the same thing over here. 0 equals negative 2y plus 8. Now, I wanted to start with this example because I think that it's one of our more straightforward examples. In other words, if I look at this equation, 0 equals negative 2x plus 6, I can use my algebra skills to solve for x. And that's half the battle because we want to find the x values and then we want to find the y values. So I'm going to go ahead and add 2x to both sides. So I get 2x equals 6. And then I'm going to divide both sides by 2. So I get x equals 3. Okay? This is the x value of a critical point that we have. And it turns out it's the only x value for this problem because when I solve this equation, I only get one number. All right, let's take a look at this equation. 0 equals negative 2y plus 8. Turns out I could do the same idea. I can get y all by itself. So I'm going to add 2y to both sides. And then I'm going to divide by 2. And I get y equals 4. Now what this means is that we have a critical point at f of 3, 4. Okay, so when the x value is 3 and the y value is 4, we have a critical point. Now, sometimes we're going to go through examples where we find more than one, but in this case, there's only one. Okay. Okay. Now that we found our critical point, let's see what we do next. All right, so we found a critical point, and now we have to find our second partials, and we're going to plug them into the equation and figure out, is it a maximum, a minimum, or a saddle point? Okay, and the equation I'm talking about is AC minus B squared. So I'm going to go ahead and find the second partials. All right, let's write find fxx, fyy, and fxy. All right, fxx means I have to go back to my x equation, my fx equation, which is right here. And then I'm going to take another derivative with x as the variable. So negative 2x plus 6 just becomes negative 2. I can do the same thing with my fyy. So let's actually write that this is our a. All right, fyy. Okay, I'm going to go to my y equation. My fy is negative 2y plus 8. my fyy is just going to be -2, and this is my c value. Okay, so I've got my a value and my c value. Now I have to find my b value. So fxy equals, okay, let's go back to our fx, -2x plus 6. I'm going to take my derivative now with respect to y. There's no y, so that fxy is actually just 0. And that happens sometimes, and it's okay. All right, and this equals our b. So we've got our a, our b, and our c, and we're going to plug it into ac minus b squared. And whether it's positive or negative will tell us what kind of critical point we have. All right, so AC minus B squared is going to be -2 times -2 minus 0 squared. Okay, now if there was ever a moment where we were going to be really careful about our signs, now is kind of the time, because whether our answer is positive or negative actually tells us two very different things, right? So -2 times -2 is going to give me a +4, minus 0 gives me a +4. Now, what's important is not really that it's 4. What's important is that it's positive, okay? So the important piece here is that it is a positive value. Okay, so let's go back up to our chart. If AC minus B squared is positive, then we're either dealing with case 1 or case 2. That means we don't have a saddle point, but if our A is negative, we have a local maximum, but if our A is positive, we have a local minimum. So if I go back and I look at my A, maybe that's something I want to highlight. All right, my A value is -2. That means I have a positive AC minus B squared and a negative A. That means I have a local maximum. Okay? So this is positive. And let's summarize this in a sentence. So since AC minus B squared is positive and A is negative, f of 3, 4 is a local maximum. Okay? Now, I intentionally wrote this out in words, positive and negative, because I know sometimes like the greater than or the less than signs, those can get confusing for us. So this is like a way for you to make it clear for yourself. But if you want to write greater than 0 or less than 0, that's also fine. Okay? All right. So let me get this all on one page for you, but this is basically like our most straightforward kind of case, thinking about how to find whether something's a maximum, minimum, or a saddle point, okay? So let's move on. We're going to take a look at a second example. This one I think is going to be a little bit more interesting. It's a little bit more algebra heavy, but it's going to be the same idea, like find our critical points, find our second derivatives, plug it into the equation, okay? So let's turn the page. Okay. Example 2 says, find all local maxima, minima, and saddle points of fxy equals x cubed plus y squared minus 6xy. So let's start off the same way we did before. We're going to find our critical points. Okay, CP for critical point. So fx equals, all right, x cubed, the derivative is 3x squared. Y cubed, the derivative is 0 because we're treating y like a number, minus 6xy just becomes 6y because the x goes to 1. Okay. All right, let's do the same thing with fy. X cubed, that derivative goes to 0, plus y cubed has a derivative of 3y squared, minus 6xy becomes 6x, because the x is a number, but the y is a variable. All right, so we've got both our fx and our fy, and now we're going to set them equal to 0, okay? We get equal 0, equal 0. Now, one thing you might notice is in this case, we have x's and y's still in the same equation. And this is where it's going to take a little bit more work for us to do, okay? Now, one way to go about this is substitution, all right? So that's where you like solve for one letter and then you plug it into the other equation and then you're able to get the letter you want, okay? So what I mean by that is I'm going to take this, I'm going to use substitution, and I really have 3x squared minus 6y equals 0, right? That's my fx, and that equals 0. And I'm going to get y to be all by itself, all right? So I'm going to add 6y to both sides. So 3x squared equals 6y. And then I'm going to divide both sides by 6. So I get 3x squared over 6 equals y, all right? And let's reduce this to be x squared over 2, because 3 and 6 reduce to 1, okay? Now, everywhere I see a y in the other equation, I'm going to replace it with x squared over 2. I'm going to do this very carefully. Okay. So I really have 3y squared minus 6x equals 0. All right, so this y, I subbed it out for the x squared over 2. Now I got to be really careful here because the squared for the y, that still stays. All right. Now this looks kind of messy, but let's take it step by step. And what I mean by that is we're going to distribute our power first. So we're going to get 3, let's do 3 over 1 times x to the 4th over 2 squared is 4, minus 6x equals 0. Okay. Now I'm going to turn this into a single fraction. So I get 3x to the 4th over 4 minus 6x equals 0. Now, I don't really like working with fractions, so I'm going to use a clever multiplier. I'm going to multiply this whole equation by 4. And when I multiply the equation by 4, my fraction is going to go away. Okay, so I'm going to multiply everything by 4, and I end up with 3x to the 4th minus 24x equals 0. Okay, so like the 4 here, the 4 here, and the 4 times 0. And now I'm going to go ahead and factor this out. That's going to be helpful for us here to help us find our x value. All right, so let's continue this up here. I can take out a 3x, and then I'm left with x cubed minus 8 equals 0. This is going to let me say 3x equals 0 and x cubed minus 8 equals 0. Now, remember, when we factor and we set it equal to 0, that allows us to set each part equal to 0. But it only works if we have a 0 here, right? So if we don't have 0, this is a no-go. We got to make it equal to 0, and then we can do this process. All right, let's solve each equation individually. 3x equals 0. I divide both sides by 3. I get x equals 0. And let's see, I'm going to do x cubed equals 8 and x equals the cube root of 8, which is actually x equals 2. Okay. So what does all of this mean? This means that the previous problem we did only had one critical point, but this question has two critical points. One where x is 0, one where x is 2. Okay. Now, how do we find the y value that goes with it? Remember that highlighted equation? We're going to go back and we're going to use that. Everywhere we see an x, we'll put the numbers we have, and then out is going to pop the y that we want. Right? So y equals 0 squared over 2. That means y equals 0. And if I plug in the x equals 2, I get y equals 2 squared over 2, which means y is 2. Altogether, this means we have two critical points. The first one is this pair, 0, comma 0. And the second one is the second pair, 2, comma 2. Okay? So we went through, this one is a lot more algebra, but it all just uses skills we learned in our algebra class. All right, so we do a little substitution, we use some algebra, and out pop two critical points. What this means for our next step, okay? So you see over here in the previous problem, we found our fxx, our fyy, our fxy, and we only had to plug in for one set of numbers to find out whether that one was a local min, a local max, or a critical point. In this question, we are actually going to have to do this twice. Okay, we're going to find our second partials, but then we're going to plug in 0, 0, see what happens there. And then we're going to go back and plug in 2, 2, and see what happens there. Okay, so let's find our A, B, and C. Okay, so A, we said, is our fxx. Let's go back up to our fx. Where is it? Okay, fx is 3x squared minus 6y. If I take another derivative treating x like a variable, I get 6x. All right, let's find B and let's find C. So fxy and fyy. All right, so if I go to my my fx, 3x squared minus 6y, and we take a derivative treating x as the number, this is going to go to 0, and negative 6y will become negative 6. Okay. Now let's find our fyy. So my fy is 3y squared minus 6x. And that derivative, when I treat y like a variable again, is just going to become 6y minus 0. Okay, so 6y. All right, I've got my A, I've got my B, I've got my C. Now let's do critical point number 1, which is our 0, 0. And then we'll do our critical point number 2. Okay, so for critical point number 1, we have AC minus B squared. That's going to be 6x times 6y minus negative 6 squared. And everywhere I see an x, I'm going to plug 0. And everywhere I see a y, I'm going to plug in 0. So 6 times 0, 6 times 0, minus, let's be really careful here, negative 6 squared gives us 36. Okay. All right, 6 times 0 times 6 times 0 gives us 0 minus 36, which is negative 36. Okay, let's go back up to our chart. Let's see what this tells us here. Okay, so if my value is negative, then it's case 3, and I actually means I have a saddle point at 0, comma 0. Okay, which is the one that looks like this. The highest in one direction, but simultaneously the lowest in the other. So we go back, all the way back, and we say, since AC minus B squared is negative, F of 0, 0 is a saddle point. Right? So not bad. We plug it in. The only thing we got to do is now we have to do it for the second critical point as well. Okay. So for critical point number 2, that is our 2, 2. All right. So we're going to do AC minus B squared again and see what we get. 6x times 6y minus negative 6 squared. And this time for x I plug in 2 and for y I plug in 2. So 6 times 2 times 6 times 2 minus 36. All right, this is going to give us 12 times 12, which is 144 minus 36, which is a positive number. Okay, so we could find the number, but it doesn't actually matter what the number is. It matters whether it's positive or negative. Okay. Okay, well, if AC minus B squared is positive, then we actually have to see what fxx is, right? So fxx, which is our A, let's see, that's 6 times 2, which is 12, which is also positive. All right, so I have a positive AC minus B squared, and I have a positive A. So let's go back to our chart, see what that means. All right, looks like case 2, positive and positive means that we have a local minimum at f of 2, 2. So let's write another sentence. Since AC minus B squared is positive, that's another way you could write it, and A is positive, f of 2, 2 is a local minimum. Okay. Now you can see why I left you so much room on this page, because it does kind of take a whole page worth of work, only because there's a little bit more algebra, and because there's 2 critical points, we have to like plug in both of those, and that just takes more space. Okay. All right. So we've done examples where we're just practicing the process, but now let's think about like why we need this in the real world, right? Who is out there asking you to find fxx and fyy, and like what does that actually help you with? So we'll take a look at these 2 word problems here. All right, first one up. So a company makes sedans and SUVs. The price function for sedans is P equals 17 minus 2x, and the price function for SUVs is Q equals 20 minus y, where the price is measured in thousands of dollars. Okay, meaning like if you get 5 for P, that's really $5,000. Or if you get like 2 for Q, that's really $2,000, not $2. Now, the profit function for the company is given by P of XY equals this long function. Find out how many of each type of vehicle should be produced and the prices that should be charged in order to maximize profit. Okay, this is exactly a scenario where we want to know how to make the most amount of money, right? This is important to companies. How do we make the most amount of money? We use calculus to help us figure out where that maximum is, okay? All right, but it turns out our steps are going to be the same, all right? So we're going to start by finding critical points. And then we're going to find our A, B, and C and figure out whether we have a maximum or minimum. It should be a maximum, but it's good to check anyway. Okay. All right, let's start. Our PX equals, all right, negative 2x squared becomes negative 4x. Negative y squared goes to 0. Plus 2xy is plus 2y. Plus 2x is plus 2. And 4y minus 5 goes to 0. So this is going to be the first one that I set equal to 0, my px. My py, I'm going to go through the equation again, but this time I'm treating y like a variable in my brain. So negative 2x squared, that goes to 0. Negative y squared goes to negative 2y. Plus 2xy goes to plus 2x. Plus 2yx goes to 0. Plus 4y goes to 4. And the minus 5, that also goes to 0. And I'm going to go ahead and set that equal to 0 because a critical point has the partials equal to 0. Okay. Now this one is going to require a different algebra technique to figure out. So I've chosen problems carefully where we have to use like a variety of algebra skills to solve them, okay? Hopefully that'll help you out on your homework depending on what kind of questions you have. All right. Now in this case, we're actually going to use a method called elimination, all right? Now, what I mean by elimination is we're not going to solve for a letter, plug it into the other equation, and then solve for that one. But rather, we're going to combine our two equations, maybe by adding or subtracting to get rid of one of the letters or like to eliminate it, okay? But before we do elimination, it's usually easiest if you line everything up in the same order in both equations, okay? So I'm going to write the first equation as negative 4x plus 2y equals negative 2. So I'm just subtracting that 2 to the other side. And the second equation, I'm going to write 2x minus 2y equals negative 4. Okay, so 2x minus 2y equals negative 4. Now, I'm going to add the equations together. So negative 4x plus 2x is negative 2x. 2y minus 2y, that goes to 0. That's where our elimination happens, okay? And then negative 2 minus 4 is negative 6. So I really just have negative 2x equals negative 6. I divide the negative 2 and I get x equals 3. Okay? So different technique than the other problem, but it looks like in this case, I'm just going to have one critical point. All right? I have the x value. I have to find the y value. To find the y value, plug it into either equation. Doesn't matter which one. Let's plug it in. Let's see what we get. So I'm going to choose the py, all right? So I get negative 2y plus 2 times 3 plus 4 equals 0. So in other words, I took this 3 and I plugged it in for the x. All right, negative 2y plus 6 plus 4 equals 0. I'm going to add the 2y to the right-hand side. 6 plus 4 is 10 equals 2y, and that gives me y equals 5. Okay. That means that P of 3 comma 5 is a critical point. Okay. Now, I'm going to leave it to you to show that this, if you use your second derivative test, like we did in the other problems, should give you a maximum. All right. But once we've checked that it's a maximum, we want to make sure that we answer the question. So it says, find out how many of each type of vehicle should be produced. All right. Well, X is how many sedans. Y is how many SUVs. But then I want to know the price for each one. That means I want to find P and I want to find Q. Okay. So it looks like 3 means that we should produce 3 sedans. Okay. So P equals, what was my equation again? 17 minus 2x. Okay. 17 minus 2x, which is really 17 minus 2 times 3. And this gives me 11. Okay. But what it means is that we should charge $11,000 for the sedans. Okay, so $11,000 for each sedan. I wish cars only cost $11,000 these days, but we're not really in that sort of environment right now. Okay, now let's find out the price of the let's find the price of the SUVs, and then I'll answer the question I see in the chat. Okay, so Q is 20 minus Y. All right, what is our Y value? Our Y value is 5, so 20 minus 5, which is 15. So that means that we should produce 5 SUVs, and the price is $15,000 for SUVs. Okay. All right, let me check the chat real quick. Trying to visualize this. Does the equation need to be simplified in each? Oh, okay. So if you want to graph this, like if you want to graph this profit function, okay, I'll actually drop a link in the chat. Or actually, if you Google Desmos 3D, okay, if you go to Desmos 3D and you type in this equation, it will show you a situation. It will look like this upside down cup we had over here. All right. But yeah, Desmos 3D is pretty cool. It helps, I think, helps with the visualization. So you can kind of confirm for yourself when you're doing your homeworks, like, okay, I think it's a maximum. If I graph it, do I still get a maximum? Okay, great question. All right. So this is an example of like when we would want to use this in real life, right? But let's take a look at another example. Profit is important, but sometimes revenue and cost contribute to that as well. Okay. So second question. A firm produces 2 types of earphones per year, X thousand of type A and Y thousand of type B. So maybe in today's world, we might think about this as like X might be the number of like the earbud types, and then Y might be the kind that's like the noise canceling over the ear kinds, right? So maybe those are the two types of earphones that they have. But X is measured in thousands. So like if we got 3X, that would be, or 3 for X, that would be like 3,000 earbuds. But if we got 5 for Y, that would mean 5,000 of the over-the-ear ones, okay? So a company is producing these two types of earphones, find the maximum profit. So again, we want to know about that profit, right? How do we make the most amount of money? If, we're not given a profit equation this time like we were last time, if the revenue and the cost for the year are given below, okay? So this is going to require a little bit more work up front. And I'm going to put this as like a step 0 over here. Okay, I know that kind of looks like a donut, but it's like a step 0. And that is we want to find our P of XY. All right. Without finding that profit function, then we aren't going to be able to find the maximum on that particular curve. But luckily for us, P of XY is equal to our revenue, R of XY, minus our cost. Okay. Now, it's important that we do revenue minus cost and not the other way around, because revenue is like how much you're bringing in, and then the cost is like how much you're spending. Okay. So I'm going to throw this equation minus this equation down here. And we're going to get 2x plus 3y minus, we're going to open up a parenthesis, x squared minus 2xy plus 2y squared plus 6x minus 9y plus 5. And I want to be really careful here, because if I don't distribute that minus sign, then I'm going to get the wrong profit function. And then all the work I do after that is kind of meaningless, okay? So 2x plus 3y minus x squared plus 2xy minus 2y squared minus 6x plus 9y minus 5. Ooh, that's a lot of signs we need to change there, okay? Now, I'm just going to take a moment and see if there's any like terms that I can combine, and I'm going to move the terms that have the higher powers to the front, okay? So I notice I have a negative x squared. That's the only one of that type. And then a negative 2y squared, right? So these ones are good. Now, I have terms that contain x. 2x plus minus 6x is minus 4x. I have 3y plus 9y is 12y. And then I have my 2xy minus 5. Okay, so plus 2xy minus 5. Now, do you have to simplify before you take your derivative? No, but I feel like if you don't, you're going to have so many more terms that you have to combine at some point, and it might just feel like more work later on, okay? So that's your step 0. Step 1, let's go ahead and find our critical points. And we're going to find them the same way. We're going to find our px and our py, and we're going to set those equal to 0. So px is negative 2x minus 4 plus 2y equals 0. Py is negative 4y plus 12 plus 2x equals 0. Now, we've sort of seen 3 different techniques so far. I hope we kind of recognize this looks most like the last example we did, where we might want to use elimination. And in particular, I notice I have a negative 2x and a positive 2x. So I can just add those equations, and then the x's are going to go away. But let me sort of write them in the same order. So negative 2x plus 2y equals 4. And then 2x minus 4y equals negative 12. I get negative 2y equals negative 8, and y equals 4. And this is good because it shows us we really just have one critical point. And if you go to Desmos 3D and you graph this big old equation, you'll find that you have, kind of a dome-shaped thing again, all right? And the y value at the top there, and I think you can kind of click around and see it, but the y value there should be 4. All right, we pick one of the equations, doesn't matter which one, to plug back in to find our x. I'm going to choose the px one. And we get negative 2x minus 4 plus 2 times 4 equals 0. I get negative 4 plus 8 equals 2x. 4 equals 2x, and x equals 2. All right. Same idea. I'll let you confirm that we, in fact, have a maximum there. But this question isn't asking you find the x and y value. It's actually asking you to find that maximum profit. So what this means is we need a sort of final step here where we take the x and the y, we plug them back into the profit function because they want to know about the maximum profit. So we take our x, we take our y, we plug them in, it will give us the profit that we have. That'll be the most, okay? But keep in mind that number is going to represent millions of dollars. Okay, so if we get 2, it's not like you made a profit of $2, you made a profit of $2 million, okay? And this x equals 2 is 2,000 of like the in the earphones. And this 4 is like 4,000 of the over the earphones. Okay. All right. Did I leave myself enough room? I did not. So we're just going to take this. We're going to resize real quick and I'm going to squeeze it at the bottom. Okay. So step 2, we're going to find P of 2 comma 4. All right. So P of 2 comma 4 means I have negative 2 squared minus 2 times 4 squared minus 4 times 2 plus 12 times 4 plus 2 times 2 times 4 minus 5. Whew, that's a lot. If you're going to type this into your calculator, just kind of double check it, make sure you're plugging in everything correctly, but you should end up with 15. Okay. Now the 15, again, that's $15 million. Okay. So your max profit is $15 million. All right. So that brings us to the end of this section. Again, some of this might have been review, but I never know how in-depth other instructors go. So I just want to make sure we've covered this because the next time we meet, we're going to talk about a different method for finding a maximum. Okay. So I'm going to pause the video here.